Okay.
Okay, so we're ready to start part 2 of tutorial 3. Amen.
Thank you. So for the benefit of those who came early from lunch, I'll show you a candid demo. So I could have put this slide as well. So what I show here is a benchmark, which was actually at lunch. We had this discussion about 2016. This was submitted to 2016, the competition. So this thing here, SNCF model check, bound and model checking. And this is about like checking safety of French railway interlocking systems. So if you're ever going through with the TGV, you might think about this because the company who produced this is really checking this and they require proofs. So this is why this is a cool benchmark. Also, all these benchmarks they submitted the hard ones. In that competition, no, none was solved. Okay, and this is the smallest one, which like BMC depth 7. So this can now be solved by KISAT. But the reason I'm showing you this because it has, I explained a bit like if I would run it, like you would see how this scrolls. But like because it takes, as you can see, 1,500 seconds. So that's why I'm not doing this. But I want to show you a bit the output of KISAT. So because if you're kind of a bit of want to peek into the solver, what it's doing, maybe this is the most important part. So that's why I want to explain this. So the output here is you see these are columns. So here at first column is seconds. Here's the main memory use. This is the average decision level. This is the number of clause database reductions. This is an important one. This is always increasing. These are the conflicts, right? You see them here. These are the remaining learn clauses, and here at the end you see the remaining original like irredundant clauses. And last not but least, this is why I'm showing this. This is a number of variables and its percentage compared to the original variables, right? So like after 7 seconds, somehow magically, and I show you this already reduced like 80% of the variables, and this was over 1 million, right? So this was a reduction of the search space of 2 to the power 800,000, right? And that's of course like due to variable elimination and other things. So let me show you this a bit. Um, Actually, this benchmark is strange. So they have a kind of a bad encoding because after unit propagation on top already 30,000 variables are gone, like 300,000. But this is how industrial benchmarks work, right? So they encode something and then 300,000 variables are just completely redundant. Um, then this is this new improsetting method. So these letters here describe like what happened, right? So this is this concurrence closure. I'm going to present on Wednesday a paper on this. This is really effective, as you can see. So um, it removes like identical circuit structure in these benchmarks because that's also what these people often do. They just have redundant circuit structure in this encoding. Um, then there's like equivalence literals reduction, and twice, then there's a semantic SAT sweeping. This, in principle, subsumes what we do here, but it's way more expensive. So this is why this is preempted. So it will work only on some variables, and then later will be resumed. Okay, and then again to equivalence literal substitutions. And now comes the part why I'm showing this. This is our BVA, and you'll guess why I called it F. Well, for factorizing, right? And B was already taken for block clauses, so it's F for factorizing, right? And you see what's happening here? This is not a traumatic case, but it's industrial benchmark. You see, there's not expected some sort of like pigeonhole or something in this, but like you add like 20,000 variables, right? And you remove what is this 70,000 clauses, right? And right, and then this goes on. Then CDCL kicks in, and even after a couple of conflicts, you learn new units. So all of these are unit clauses learned, and that of course reduces the. Oh, forgot one important one. This is variable elimination. So this one reduces. This is the biggest hammer we have, right? And this removes another 30% of the variables. All right, and then CDL starts, and it learns a unit. You see this goes down only by 2. You learn a unit and you apply it, so 2 variables go away, and so on, right? So this is, and then at one point, you start here with another round. This is now in processing, right? So like all these preprocessors are kind of preempted if they take too much time and resumed. And particularly, we learned new unit clauses, right? So we simplified the formula. So it's clear that we want to do, for instance, this factorizing again. Okay, and it's really happening here even, as you can see. So not many variables were introduced, but you see there's some reduction here. Like, yeah, what is it? 50 large clauses get reduced, and these are the binary clauses. Also 200 get reduced by adding like what is it, like 20 variables, right? But this means this BVA is actually like happening after a while and should be triggered once again. Right, and then you continue doing this. At the end, you see after like half an hour, almost this is down to 5% of the variables. So you started with 1.1 million, and at the end we find the empty clause. And I think this is typical for such industrial BMC examples. I mean, like maybe Alex can confirm this. This is like, and some people run this for days, and it would look similar, right? Okay, this is what I wanted to show. There's here in this, this is our hard benchmarks we looked at before. And right, so these are these 52 benchmarks I selected. And there I also had the log files. And then I grabbed for the occurrences of this F line, right? And you see, well, it's also happening all the time, right? Like in processing kicks in, and you actually this happening, this PVA. So initially it adds 24% variables, right? But then later in the same benchmarks, it gets down to 95, right? And so on. Okay, so this is a way of to interpret and understand like what the solver in these algorithms are doing. Okay, now I need to go back to my slide. I'm still running, yes. Okay. Okay. Here. Okay. Sorry. All right. So this was another window. Sorry about that. So now I have this like second quantum leap, which I want to explain, and I only have very few slides on this anyhow, so like four. And this motivates our second part, the local search. That's why I want to still spend these 5 minutes maybe on this one. So in 2016, actually, where this was this big like change in like where Maple was entering the scene, and this changed like the competition for 4 years. It was actually due to Chansik O proposing here this, he called it SAT unsat mode, um, which you can think of as a portfolio. So this is now how I would explain it now. Also, like I discussed this with Karim Sakala for a long time. And we now come to the point we would call it actually portfolio. So you do a portfolio within the SAT solver. How do you do that? Well, you just run like one configuration for a while, then you switch to another one. And what Chansik O figured out and this was his conjecture, and he was right. Well, of course, there should be different configurations for satisfiable, unsatisfiable formulas, right? Sounds completely obvious, right? And then he tried to figure out how can I kind of parameterize CDCL solver such it works better for satisfiable or for unsatisfiable. And he had two parameters, which Alex already described yesterday. One parameter like the restart frequency, and the other one was how strongly you smooth the score of variables, which is like how actually eagerly you look at recently interesting variables, so you kind of summarize more over long term. And the surprising thing is that for SAT, when restarts were introduced back in the 90s to SAT, the argument you need this restart for satisfiable instances, but it's actually not true. You can actually almost never restart in set for satisfiable instances. For unsatisfiable instances, the opposite. So you should maybe restart even after every conflict. Okay, it's completely opposite from the original intuition. And we know this only empirically. There's no theory here, but it's really true. It's completely true. Like after like now almost 10 years, it's an empirical fact. And for satisfiable, this is more clear. You want to have a slow decay, so the scores are bumped, right? And they slowly go down with an exponential moving average. and you want to very slowly get them down. And this is good for satisfiable instances. So like a variable which was important for a long time should stay sort of in the interest. While for unsatisfiable it's the opposite. So they really always eagerly try to find the most recently used variable. And these are the two main parameters. And then the only question is when do you switch between these two modes? So this was, I don't think I have the picture here. Maybe I need to go back for here. So this is the jump which you, well, not there, which you see kind of here from these solvers to the maple solvers, which is this line here. Okay. And all right, so this was one of the quantum leaps, and another one was this. We did actually two groups independently. Xiaowei Chai had exactly the same idea, like also like tried to get to this point where we are now 10 years ago, and myself I also started to look into this. So the point was, can we combine local search with CDCL search? And we finally managed together. Like there were also that year, this was 2020, 3 solvers which used this idea, and they came on almost at the same spot. KISAT was slightly faster, so I won. But the other two, Crypto Minisat and this version Reason LS, I think it was called, were very close. And here was the idea. So it's called target phases. So you maximize the consistent trail. So you turn the idea of finding a satisfying assignment into a maximization problem by saying, okay, the partial assignment I have on my trail is something, the length of this partial assignment is something I want to maximize, right? And of course, it has to be consistent. So after propagation, it should be not get into conflict. And that's what we call then a consistent trail. And when we get a newer, larger consistent trail, then we save it. And then whenever we make an assignment later, we always pick the assignment from this largest consistent trail. So we're extremely sort of like stubborn here, right? Maybe some of you know this phase saving, safe phasing, or phase saving, or assignment phase saving. This is way more stubborn. So you just always take the same partial assignment, you make it longer and longer and longer, right? And this has dramatically positive effects on a satisfiable instance, but it actually also gets stuck. And then comes the classical AI technique. Well, when you do search and you do this intensification, you also need to do diversification. So if you and how do you now do a diversification? Well, you sometimes in a while just forget the best consistent trail, right? But then you still need to figure out like what would be the values I should assign to those variables I pick as decisions. And you can do random. You can then always pick true again, always false, and then start again counting for the largest trail. And last but not least, and this is the motivation for the rest of this hour, well, you can also just lose local search. You take your maximum consistent trail, you give it to a local search solver and tell the local search trail, make it bigger. Okay? And then when it succeeded and actually satisfies the formula, well, you have a local search solver getting you satisfy an assignment, which actually happens. So the CDCL solver gives a good starting point for the local search solver. And if it fails, well, you get from the local search solver these values it would assign as the starting points for your new phase or values decision heuristic. Okay, so this is how both Xiaowei and I came to we had the same idea how to add a local search solver to CDCL. However, it only really worked when we added this target phases. So this combination here, target phases plus local search in 2020 was giving us this new jump in 2020. And of course, mostly on the satisfiable instances. So I have here from our paper, so this is from this paper here, chair paper, the plots. And I need to, so this is the default where you do both these target phases and you also resetting these phases. So I call this refacing, right? Because you're saving the phase is the value assigned to variables, and so refacing means okay, I forget completely somehow what were the values I used in the past. I'm now picking a new set of variable values. All right, and no rephase. This is this red one, right? This is somewhere here, right? So only target phases don't give you that much, right? If you always target, this is actually not bad, right? Like I forgot to mention, this was the reason I explained this Chansik O um, paper approach, this mode, SAT and unsat mode, that only in the SAT mode, this target phases, of course, make sense, right? Because there you want to really want to think about like a satisfying set minus. So you switch these target phases only on in the um, in kind of in the mode where you go for satisfiability. And if you do it always, well, it's almost as good, right? You're losing only a bit. And of course, you're losing only on the unsatisfiable instances. And if you're not doing any of it, you see, this is much worse, right? This is kind of before 2020, right? And you see, of course, a even wider spread on satisfiable instances. So these are only the satisfiable instances. And there you see this always target would then win. So the first two actually swapped the place, right? Always targeting is better than once in a while sort of like not doing it. All right, and this is a huge difference, and in a certain sense, like in retrospective, it's also not that surprising, right? Because on satisfiable instances with heuristics, you can much easier win than an unsatisfiable, right? Because you just need to some kind of tell the somehow either explicitly or implicitly tell the solver what are the right values you should pick, right? And then you get sort of if you pick always the right value, you instantly solve the formula, right? Okay, so this was the big last quantum leap before BVA, right? And it's the motivation why we want to look at local search. You see it also here. If you're not refacing right here, this is without refacing, but still targets, you're actually losing compared to kind of resetting the faces once in a while, right? Which is also intuitively clear, right? If you kind of stop on, always pick this largest consistent trail, well, you get stuck, right? And so you need to sort of reset it once in a while. Okay, for unsat, the spread is of course not that much, and in particular, you see also that actually the always target is worse. And okay, and we have a similar picture for the other years, but as I explained also the other maybe in the discussion or before this morning, um, the winner of that year, this was 2021, so the winner of 2022 was Kisat, has of course always an advantage, and 2021 this advantage is still there a bit, right? Okay, this is why I want to look into local search. And before I like explain a bit history and also technology, I want to first go through with you this algorithm that you understand what I mean, right? And then we'll talk about the history and everything. So local search and CNF. I mean, local search was invented in other contexts, but like for CNF, it's very simple. So this is the kind of simplest algorithm you can think of. So you have a CNF, okay, and then you pick a random. Now it's important this word total assignment. So when we do CDCL or like these target phases, we always have partial assignments, like the trail, right? How far you get deep. So here we have a total assignment. And this is actually like a nice part of this because implementation wise and also like when you think about it, it's different than in CDCL. Okay, so this is our total assignment. And then you simply check whether it satisfies all clauses, right? Okay, and you have an infinite loop here where you just check whether the clauses are satisfied. And then if not, I mean, this is the most basic one, you just flip a variable, right? You pick one variable, can pick it arbitrarily, and you flip it. And flipping is here formally defined, but you know what I mean, right? So it's just like flip the value from 0 to 1. Okay, so this has a long tradition, and it's very interesting. This is so I asked this question back to some people from the CADE community, like a deduction community, Y was actually kind of like core theorem proving, not a topic in AI anymore. Because in the early days, of course, theorem proving was an AI topic, right? Like in the 60s, McCarthy and these guys. But then at one point, probably around the time when the CADE conference started, um, like people didn't publish there. At least sort of so knowledge representation and this work was still published, but the core theorem proving people did not publish in AI conferences. And I don't know why, actually. So I have some conjectures, but last time I gave this talk, I couldn't come to the point figuring out the right conjecture, but it's like that. So if you look at the sort of the most cited people in the community, and if they have kind of a more theorem prover, like technical agenda, then they're not publishing in the AI conferences. Now comes the point. Well, for SAT, this was not true. SAT always was and stayed in AI, right? Through all these years, like from the beginning, 80s and 90s. However, in the 80s and 90s, actually all they did was local search, okay? So this is very funny. So the reason why SAT is still a core topic in AI, and now, of course, also with our sort of more CDCL kind of reasoning was because of the history I'm going to show you, these algorithms which you see some high profile AI people also mentioned here in the, when I do the references. So this is a sort of interesting historical observation. Okay, and by the way, because the SAT conference started, this is the reason why the SAT conference always had like, when I entered the SAT community, I was a verification person. I was shocked that like 1/3 of the people are strange AI guys, 1/3 are verification people, and 1/3 are the theory guys. I don't understand, right? And so it's actually nice to be here because, and you now know probably why, right? Because particular local search stayed there in AI for all the time. All right, so let's look at the history. So this is, of course, not working, right? But it gives you a flavor of what you're doing, and it already shows you a flaw, right? What's the flaw? Well, it can never prove unsat, right? So it just returns a satisfying assignment. So this local search only works for satisfiable instances. But already with these target phases, I gave you an idea why this might also be interesting for people who want to do proofs. And we saw actually in your talk also an argument why you want to maybe use even sort of incomplete algorithms for like giving good guesses or something, right? Okay. So, but there's still some sort of completeness, and this goes back to Holger Hoos, which is one of these big AI figures in our community. And but let me go from the top. So I want to explain completeness with this slide, which is the last bullet. But let me start from the. So these local search algorithm I showed you, they're incomplete in two ways, right? So they might not terminate, and this is actually if you will see like a classical way of writing it up in AI, or they return unknown, right? Which is a bit weird to me, right? But like on the other hand, I mean, this is what people in industry would do when they do BMC. They run this for 100K, right? And for K equal to 100, and then it's also unknown, right? It only can return satisfying assignments, right? It cannot do unsat. This is still one of the open problems, how to use local search for unsat. Nobody has figured it out. So this was a challenge by sort of or there was a list of 10 challenges by, I forgot, like I think it was Bart Selman and somebody else, I forgot the other person. And yeah, Toby Walsh in 2000 about so the 10 big challenges for like for SAT, and one of them was merging local search and CDCL. That part we solved with our target phases actually, but the other one, like using local search for unsat, nobody has any real idea. Okay, so these are these two incompleteness. You cannot, it doesn't work for unsat, and it it might not terminate or just return alone. However, if you look closer, and this was an insight when I prepared these slides for the first time, well, they fall into this class of Las Vegas randomized algorithms where sort of you guaranteed that this is a satisfying assignment if it returns, right? Because you're checking it. Like in CNF, there's no point returning a satisfying assignment without checking it. And so they're not like these Monte Carlo algorithms, which just have like probabilistically are correct, right? Um, and but we do have some actually some people are probably here who implemented this GANAC solver for model counting, right? There we have actually a model counter which falls here in this first class, right? And but what are applications? Well, generate test cases, hit coverage holes, right? So like configurations, whatever. There's lots of interesting practical applications where you're actually only interested in SAT. So you don't even want to know when it's unsat. It's not interesting. And there's the second part. This is why it became it remains so popular in AI. Actually, one of the most important problems in all these research areas is how to come up with benchmarks. Okay, because then how do you actually measure progress if you don't have benchmarks? So the I people were very did the simple approach. Well, they just generated randomly benchmarks, and still until today, if you want to publish in the AI conference, just take a sort of generate some random benchmarks is completely fine. And all right, so that means there's a certain class of benchmarks which might not be that interesting, and this was also my biggest reservation in the past, because these algorithms which I'm going to present originally only worked on these benchmarks, on this completely artificial and nowhere else. And this changed around, like if we get to this PropSat algorithm, which was a big breakthrough, it was also published at SAT, which for the first time I saw sort of 50 benchmarks of the competition being solved by a local search solver. And I was again shocked. So, and this is why I started to look into this. And I want to, and maybe we're at the point where sort of there might be more progress. So this is the motivation I'm showing you this. Okay, so my students did the first SMT version for that, and then another student extended this for bit vectors. And also there, it's actually helpful. And what I just showed, this target phase, is this phase assignment is, in particular the refacing using local search is very useful if you combine it here with target phases. But now coming to the main point of this. So Holger Hoos, in one of these papers where he described the walk-side algorithm, he came up with this notion here, which is called probabilistic approximate complete, or PAC. When does have such a local search solver has the PAC property? When it's complete. Well, it's intuitive, so it doesn't get trapped in a kind of a life cycle. Okay. So there's always a chance to get out of the local minima, right? And this really fights sort of the heuristics you're having. If you're following always heuristics, right, you will always follow this heuristic, and you might get a cycle, because there's no other choice than if you follow the heuristic than doing this cycle. So probabilistically approximate complete is that you have enough noise in your algorithm that at least if you kind of the noise is helpful to you, you will get out of this local trap, right? And it's a good property of an algorithm, because if you don't have this property, right, you might run your local search algorithm and it gets stuck, and there's even no chance from this to sort of get out. And we'll see this in examples. So this is an important kind of property of this local search algorithm.
Yeah, I had a question about
Yes.
the last slide.
Where? There.
So regarding the not getting stuck in local minima.
Sorry, it's noisy here.
Yeah, so regarding the not getting stuck in a local minima aspect of it. So is it the case that it can be shown that there is certain amount of a guarantee that it won't be stuck, like with some probability it will never get stuck in a
Well, the absolute probabilities nobody knows. So it's more like of a non-deterministic nature. But we'll see example now for this one.
Okay,
So
okay,
that's
thanks.
why it's more clear. So the simplest way to get PAC, okay, to get it complete is what you see on this slide. So it's the same algorithm you had before, and you will see this multiple times, right? So before we only had this part here, but now there's an if which says, well, if it's time to restart, just get a new random assignment. Is this PAC? Is complete? You're shaking your head. Not complete. No, this is complete. Why? Well, because there's a non-zero, just pick even if it's just a single satisfying assignment, right? Actually, the much more simpler algorithm, which would only do always restart, would also be pack, right? So it would be a stupid algorithm. You just guess a full assignment, check it's SAT. Guess a full assignment, check it's SAT. This guy is complete. Yeah, that's also complete. Yes. Yeah. Also, this one here is complete. However, for instance, if you're no, sorry, forward. If you kind of pick, for instance, always the first variable in the class, okay, you could do that, or like the variable which occurs most often or something. Then you see you can turn it into a complete one just by adding this thing around it. That's the argument. Okay, and that's of course like what people tried, right? So they tried to now make this thing here, pick a variable, sort of greedy with heuristics, and then you have to fight, of course, to keep it complete, right? And one way, a simple fix is, and that's what they all did, and you will see it like I have a copy of a paper. How this is done in the papers is just to restart. However, and this maybe actually touches upon something, and I'm not sure, like Alex, you didn't talk about restart. So restart is also an important topic in CDCL, and it started here in this local search domain. And what I'm showing you here is actually kind of porting some of the development we had back in the CDCL to the local search. Okay, so when do you restart? I mean, as I said, right, restarting every flip is still pack, right? But maybe not the wisest thing to do. And then one thing which comes to your mind is, well, then let's just maybe restart every like 10 flips or n flips, where n is the number of variables, and we'll come back to this because there's also nice theoretical work which says you should restart after 2n or after 3n. Okay, and this is this parameter max flipped. So you kind of flip that many times, right? And then you restart, and then you may change this max flipped, right? And in CDCL SAT solvers, there are kind of two obvious way of doing this. Minisat, for instance, had that one. So Minisat, for instance, would say, after 10,000 conflicts, okay, let's restart. And then next time, let's start after 50% more, like 15,000 conflict, right? So you have a kind of geometric increase of this one. What current solvers do is either this one. This is an arithmetic version of this one. So you increase it sort of with a constant instead of by 50%. So typically would be here something around like actually 50 or 100. Then when this restarting came around, I proposed this inner outer, which is actually still the default in Z3, but I'm not going to explain it. So I only keep it here on the slide, because if you want to know how Z3 restarts, it uses this one. Then the default one from kind of Monte Carlo simulation is this one, and I'll want to show you this with some code later. And Donald Knuth, when he was visiting us in Linz, he pointed out that he doesn't like algorithms which are called after people. So that's why he invented this new name, which I think is actually better. He calls it reluctant doubling. I'll show you this. But before explaining this different restart scheme, I want to first show you this paper, because this is the reason why I'm actually have that 1 hour for you, because it made a tremendous improvement in solving number of benchmarks. We'll see this soon. And it revived one old idea, like with class weighting. And Solimul, like the first author here, he was a postdoc with Marijn Heule. He hacked my solver YALSAT, and it's like very complex and complicated, as you will see. So what I'm saying here is these ideas which are in here, they need to be distilled and made more clean, and then we'll get a way better local search algorithm. And in that paper, this is the original algorithm they have, and this is the flavor how people in the AI community, if you're ever going to read one of the original papers, write down this local search, and that's why I'm showing you this. Without you don't need to understand what's going on here, but this is similar to sort of like flipping something. Here, it does max tries. So this is a little bit weird. So after max tries, it gives up. So it returns unknown, right? Or no SAT. So I completely dropped this outer loop. And so what's this inner loop? Well, this inner loop is just the time you take until restart. And they also, in the AI papers, they just use a constant here, which is actually not in my implementation, also not the extension he did, but this is how people describe it in the AI papers. Okay, so this here is the kind of restart is happening. You pick a new alpha, and the outer loop, you just give up after a while. So I actually never understood why they have this outer loop. Okay, here is the way in my pseudocode, but it's exactly the same, and we'll come back to this later. So this is an algorithm here. It's called DDFW and was invented by these people in CP 2005. And the reason why we're looking at this is because Marijn tried all possible implementations of local search on this Pythagorean triples problems, right, where it's still SAT, and also in other like matrix multiplication problems. And that algorithm worked best. And but the original implementation was not good. And so he put his postdoc on like of improving this algorithm. And we'll come back to this later. Okay, in the outer, I want to skip. So I want to show you the Luby, which Knuth calls reluctant doubling. So this is the base, kind of the multiplier you take, and you multiply it by a base interval of 512, I think, in this example. And after that many conflicts, you would restart, for instance, in KISSAT, right? So first you would start after 512, then and after 1024, then in 512, 512, 1024. Oh, then I double it, 2048. And then I'm going down again, right? So it has this fractal nature that you kind of always get to the peak, and then you kind of repeat what you did before. You did get to the peak. Okay, so you already get an intuition. This is kind of log n slower than a geometric increase. Okay, but it has this nice effect, if you look here, for instance, that it still has very frequent restarts. Okay, but you're only paying for this by, at the worst case, extending sort of the time before you hit, for instance, here, the largest one of 32, by a log n factor, so by 5, right? And that's why this is now the standard. If you don't know how to do something like in intervals, you can either do the geometric scheme, right? Then you pay a constant factor, but you don't get this fast repetition of small intervals, right? Or you take this one and then you pay in the worst case only by log n. So this is why this is the default for all this kind of, when you have do some interval and you don't know what to do, just use the Luby or reluctant doubling. This is the original code for this. Never understood, just copied it. Okay. This is Knuth's code, okay? So when we explained this to him, he came up with this. This is bitwise, bit hackling. So you just need to keep a state, and then you kind of, because all this, it was 64-bit number, right? And then this will never like overflow. And then the lowest one here, the right one here, is your 1, 1, 2, 1, 1, 2, 4, 1. This is your Luby sequence, right? All right, so this is actually implemented in the exercise you're going to do. So you don't need to implement this, but we'll have that one as a base interval. Okay, now let's come to the first kind of really interesting breakthrough, which also motivated actually theory people like Papadimitriou and Uwe Schöning to look at this. Okay. It looks almost the same what we had before, right? Before there was like pick an arbitrary literal, and then you see, when I say pick an arbitrary literal, you would attach usually some heuristic with it, right? But this thing here now doesn't pick an arbitrary literal. It first picks an unsatisfied clause. Yes, because if the formula is not satisfiable, there has to be a clause which has all its literals false, right? And then what they and then Papadimitriou and the others, of course, also agreed to this, was, okay, I can just actually pick uniformly a random unsatisfied clause. I need to fix that clause, right? Okay, and then I need, if I get to a satisfying assignment, I need to flip a literal in that clause, right? Uniformly random, right? And this, of course, is, if you think about it, way better to implement. You're not like at every flip go over all the formulas. You just pick randomly an unsatisfied clause, and then in that you pick, actually you can pick a random literal. Okay? So this is the first invention. It's called focused random walk. And then there are these two papers, which I have to admit, I need to look at my theory people in the room, because I asked Jakob, and Jakob said he never checked the proof of this. Mina, did you check the proof of this? Yes. So this is what I expect. Anybody here in the room would check the proof of one of these papers? Okay, so I still need to find a theory person in the SAT community who understands this and can explain this to me. But anyhow, so what they do exactly what I just explained. This is the same algorithm on the previous slide. But now the point is they have two theorems. So Papavenitro had a theorem which says if you start with a CNF who has only binary clauses, then you pick here as restart time 2n, okay, right, 2n number of variables. Then your expected running time of this algorithm, if the formula is satisfiable, is quadratic in the number of variables. This is kind of amazing, right? So this algorithm with the is polynomial, right? Well, we know that 2CNF is solvable in linear time, but still, right? This is a local search algorithm which just needs 2n restarts, and actually very few restarts, like every 2n, and then you have a quadratic running time for expected running time quadratic. Now, Schöning has this famous algorithm. Now he lifted this to 3 SAT, and there he got off from the exponent, from the base of 2 to the power n, he got off something. I think like I forgot even, but like it's now 1.4 to the power of n, right? And also with an like in the expected running time, right? And that's also the interesting thing, his time to restart is 3n. So of course, this is why it's a 2-page proof, and there's some combinatorics. In the end, it falls out that you need to fix this to 3n in order to get this 1.4 to the power n expected runtime on 3 SAT. Okay, so this is interesting. Why? Well, because you see there's a detour through theory, and then people in the AI came back and implemented this in for real. I mean, originally only for these strange random instances, right? But as I explained already in 2012, we saw that it's really working also for industrial. And what I want to explain, because we're going to implement these functions, actually complete them. So there's already code, but it's not working in the exercise. I need to explain here this terminology. It's actually very intuitive, but it also shows like how you can like an attack angle on this problem. So what's make value? Well, make value is easy to understand. So make value, so you take a variable, right? Remember, we had a total assignment, right? So that means the variable is assigned to 0 and false. And so I can actually flip it, right? So you don't need to say I'm assigning it to which value, I just flip it. Okay, so these algorithms work on variables, not on literals. In CDCL, you always need to kind of work on literals, right? But here the heuristics are all kind of more variable-based. Okay. Ours hopefully still working. And okay, so make value then simply checks for one literal and one assignment whether how many clauses get satisfied if I flip the value of this assignment, right? So it's very simple. You just look at the clauses which are unsat currently in alpha, right? And which contain the literal in the literal for the x in such a way that it's false. All right. So this is the make value. How many clauses do you make if you flip it, right? And then what's the opposite? Well, it's down here. How many do I break? And for that, we need a helper function. This is this critical clause. So what's a critical clause? Well, how can I break a clause? I can only break a clause by flipping a variable if that variable is the only satisfying literal, constitutes the only satisfying literal in the clause. Okay. And then it's a critical variable or critical literal, right? So simply break value is just the number of clauses for which this variable is critical, right? Okay, and now you can already think like what would be a good heuristic to pick a literal? Well, you see it on the bottom. So if you think of it, you will immediately get this heuristic, right? It's kind of the cost. So if you think, if you're a machine learning person, you would think it's that. So how many do I make and how do I many break? This is the difference. And then of course should maximize this, right? This is we would call it a reward-based scheme, right? This is the reward you get by flipping X. Okay, it's just the make value minus the break value. Okay, so just to reiterate this, because this is really one of the, I think, technically interesting, most interesting insights on this local search. So here, just with an example. So here's the current alpha, right, with four clauses. This should be 4. Too many typos in my slides. And right, and red means, oh, sorry, apologize for red blindness, red-green blindness people here. So the box actually means also satisfying. So it's a box, and green means satisfying, and no box, and red means falsifying. So like you see, this is an unsatisfied clause with X in it. So this means you will make this clause, right? This one is critical, right? If I flip X, it will become broken, right? So, okay. So this is critical, and this is make minus this one, which is broken. And these guys are double satisfied and triple satisfied. Actually, we looked at this double satisfied already this morning, right? And they really don't change the score in terms of unsat clauses. It's only the first two which are interesting, and they would just change the role, right? So the first one is made, and the second one is broken, and the first one actually becomes a critical one, right? That's also interesting here. Okay, now this is what Selman and Levesque and Mitchell did in AAAI 92. And this was kind of the first sort of more modern local search algorithm. So you remember that by picking the total assignment, then there's the infinite loop. Of course, they described it differently with this max flips and max tries, but this is what it boils down to, okay? They had already restarted to keep the whole thing actually pack complete. And then this is my reformulation, how you would do it nowadays with sort of everybody doing machine learning, right? So you just do an argmax for the reward, right? The reward was the make break value and just maximize the reward, right? And that's what you pick here as candidate set. This is capital, this is no typos. You pick all those variables which have the maximum reward, it might be a set. And then from this set, right, you pick uniformly random one variable. Okay. Now, for instance, there's an interesting question. What if you drop this restart here? Is it still pack? And I think it's not, but I didn't find the literature. Holger Hoos has some elaborate discussion on this, but for the GSAT, he's not having it, so that's why. All right, practically, they kept this restart because it works way better. So this is why there's an empirical hint that you need this to get it back. All right, now, but remember, we had this focused idea, right? What also Papadimitro and Schöning used. And they introduced this like a year later, like Selman and Kautz, and in a slightly awkward way, I would say. So that we will see later the simpler version. And I claim this, what you see here, is similar to the DDFW algorithm we, like Marijn and his co-authors, used. And you will see like in 1 or 2 slides further down that this can be completely simplified and actually made faster. And this is what I'm hoping we will get to in a couple of years maybe. Okay, so they have this suddenly this fixed magic constant. So Alex was yesterday talking about this magic constant here. So this like actually this is like 0.5, so 50%. And then with this 50% probability, they would do like this a focused search we said before, like where you pick simply a random falsified, unsatisfied clause, right? And then in that clause, you pick an arbitrary literal, and then you flip it. Or with 1 minus p probability, you just do this argmax, so maximizing the reward, right? Yeah, and of course, like this remains packed if the original one was packed, because like adding this probability and doing something with a non-zero probability here, right? Like if this is always done at the end, then this is completely fine. And that was actually improving the original version quite a bit. But now this is the simplified version of what we just saw. This is called WalkSat, and actually all the modern algorithms have what's called a WalkSat architecture. So this is the architecture of like the local search algorithms I have implemented. All right, so you should see almost everything. You should know almost everything. So we have this infinite loop. You check the restart. Then you pick a random falsify clause. This is the focus part. And then you select the literal in this clause. And there's something complex here. So next slide, right? So they have a greedy heuristic for picking this thing here. And then you flip it. Okay, so compared to the previous algorithm, this is sort of using this focused random walk idea. And well, that thing is on the next slide. That's also more interesting. But unfortunately, this one is still complex. So this is the literal selection. So giving a clause and an assignment, and you know the clause is false. Try to find a literal you flip in that clause, okay? And they have actually 3 outcomes, right? So they give a set, and they first check greedily whether there is a literal for which you don't have to pay anything if you flip it. Okay, if you have literals in the clause which flipping it doesn't break any other clause, then it gets into this first set. And if this set is not empty, they would greedily, this is a greedy step here, they would greedily flip a random literal out of this where you don't have to pay anything locally. Okay, and then again, this argument with a magic constant, let's say 50%, with 50% probability, you return here an arbitrary uniform selection of literal. And then the last one, then you do an arg min now, not arg max, okay? So now we only optimize the loss. So this was an important invention, which is really also empirically justified. Remember before, it was the reward make minus break. And now with this algorithm, they only minimize the break, like only those which you actually destroy, which you break, right? You completely forget the make. And actually, before I prepared these slides, I didn't know why there's still a hidden make kind of bias in there. Does anybody see that? Well, I was teaching it in class and then gave a summer school talk now the 3rd time. Does anybody see why is there a hidden bias towards literals with a high make? Mike?
Because of the clause selection, you're always selecting a clause that's falsified. So you're going to be making at least one.
Yes.
And then trying to break nothing. So yeah.
Yeah, yes, it's almost it. So my argument is the following. So if you have a literal which is a high make count, then it occurs in more unsatisfied clauses. So if you pick a clause uniformly, there's a higher chance to pick those literals with a high make. So it's very funny that this sort of this focused random walk has a bias towards picking literals with a high make. Okay. And that was until 2012 kind of the state of the art. Like we'll see a little bit more like about clause weighting later, but here are like all these like additional things they put into this. And there's a book by here on top. There's a textbook by Holger and Stützle, Groß and Stützle, and this textbook has all these like ideas from the 90s summarized in the textbook. But it's of course now 20 years old. So, all right, and then maybe you've heard this. The most interesting idea and also flaw of this local search, right? What's the flaw of this local search, right? You're flipping forth and back all the time, right? Then you get to another one, but then you get again stuck. You're flipping back and forth. And the obvious way to avoid this is to say, I'm not allowed to flip, for instance, the last literal I flipped. Or I keep a list of 10 literals, and I'm not allowed to flip the last 10, right? Okay, so this is one way of kind of getting more greedy or like avoiding this. Then there are like like some papers, and actually this is just a selection, right? There are like, as I said, like 40, 50 papers. So they do ties broken by age. This is kind of an implicit like score, which is similar to this taboo. And